In the lecture today, we will learn vertical distance measurement, which is also called leveling. The purpose of leveling is trying to find out the elevation of one point on the Earth. The elevation is actually defined as the vertical distance of one point above or below an arbitrarily assumed level surface or curved surface. In general, we will set the mean sea level, MSL, as the base. So with MSL, we can find out the elevation of point A would be the distance from A to the mean sea level. And the elevation of B will be the distance from point B to MSL. In addition, the leveling can also be applied to find out the elevation difference at any 2 points. For example, from point A to point B, the elevation difference is set as the distance between the two level lines across the 2 points. In leveling, mean sea levels are commonly applied as the reference-based surface. However, the mean sea level along the whole Earth is not constant. It usually varies along the coast. In general, Pacific is almost 2 inches higher than Atlantic and Gulf. In North America, we will use the US system, which is the National Geodetic Vertical Denton System, and the system was developed in 1929. In this system, we define an extended network of benchmarks, which will be a set of the points with known elevation. And the elevation of these benchmarks are also updated periodically. So in the leveling, we need to check with USGS or NGS for the current elevation of the benchmark, and also check between two known benchmarks to verify the elevation differences. For the vertical distance measurement on the Earth, there are actually two factors affecting the results. The first one is the curvature of the Earth, and the second one is the atmospheric refraction, which affects the line of the sight. The figure here actually demonstrates the elevation difference between 2 points A and D. Ideally, based on the assumption about that the Earth's surface is spherical, if A and D are aligned to the same level line, then their elevation difference would be 0. However, in the actual measurement, usually we will put in the satellite or leveling at point A, and then we will set a tangent line at point A. And then we will observe that the elevation at point D will be the distance from D to E. In that sense, you will actually observe an elevation difference between A and D, but it's different from the true elevation as what is defined based on the surface of the Earth. In this case, we can actually find that there exists a relationship between the distance from A to D and the arrow from D to E. We know that r squared, which r is the radius of the Earth, plus the distance from A to E as AE squared equal to the distance from the center of the Earth to the crossing point E, that is OE squared. Also, we can see that OE is O to D plus the distance from D to E. O to D, the distance from O to D is just the radius of the Earth. And we define that D to E as an error from the curvature. That is set as C. So we set a C here, which will give us the equivalent equation as R plus C squared. And that is R squared plus C squared plus 2 times RC. And C is just defined as the curvature error. We can make some further analysis about the curvature error. From the previous page, we know that R squared plus AE squared equal to r squared plus c squared plus 2rc, and we can actually cancel r squared on both sides. That will give you the value as ae squared equal to c squared plus 2 times rc, and this is equivalent to c equal to ae squared over c plus 2r. And we know that r is the radius of Earth. And usually it's set as 3,959 miles or 6371 kilometer. And we can see that for the distance measurement, usually the curvature error is much smaller than the radius of the Earth. In that sense, for the part at the bottom, we can say that it's approximately 2r. We will ignore the part for the curvature error, which will give you the estimation of the curvature as ae squared over 2r. And this is a simplified equation for the curvature error estimation. If we say that ae is measured in miles, which we will replace this one with m, then we will have the updated equation as c equal to 0.677 m squared, and the unit for this one is feet. If we say ae is measured in kilometer, say that we use another letter k, then we will have c equal to 0.0785 k squared, and the measured unit is meter. So in that sense, let's go to check one example. Assume that we are given the value of ae as 100 feet. It wants us to find the curvature error. So for the solution, first let's convert ae to miles. A is 100 feet is converted as 0.0189 miles. And then we can call the first equation to find out the curvature error, which will give you the value as c equal to 0.677 times 0.0189 squared. The result is 0.00024 feet. Compared with the length of the distance from A to E, this error can almost be neglected. Usually the curvature error is very small. The second error we'll consider is the term caused by the atmospheric refraction. This one will usually change the line of sight for the measurement. Ideally, the line of sight should be in a straight line, and it will be the same to the horizontal line at point A. However, due to the air pressure, temperature, or geographic location, the true line of sight becomes a curve, which will be shown as A to E in this figure. And we can see that due to the impact of the atmospheric refraction, the true reading for the elevation at the point D will becomes B to D. And we define that the part from B to E as the refraction error. And from B to D, it will becomes the combined error of curvature and refraction. Usually the refraction error B to E is only 1/7 of the curvature error. So B equals 1/7 of D to E. That is 1/7 of C. With that, we can find that the combined error is BD equal to DE minus BE. That is C minus 1/7 C. It's 6/7 C. From our previous analysis about the curvature error, we know that the curvature error is the function of the distance from A to E. We can apply the similar equation here, as if A to E is measured in miles, we will have B to D as 0.514 m square, and the unit is feet. It could also be 0.0675 k square. The unit is meter if the distance from A to E is measured as the kilometers. So that's the way for us to find out the combined error from the curvature and the refraction. With the combined error, we can then introduce a direct leveling method to measure the vertical distance between 2 points. The figure here shows how we measure the vertical distance from A to B. In this figure, we can draw 2 level lines which will cross point A and point B. And the difference between these 2 lines is the vertical distance, which we define as capital H. We want to find out the value of capital H from this experiment. In the experiment, we will put a rod at point A and a rod at point B. In addition, a leveling transit will be placed in between. From the leveling transit, we will observe the readings at the rod in the point A and the reading at point B. We see the reading at point A is HA, which we will have the observations at A, and also have the observation at B as HB. And we know that the readings comes from the horizontal line from the leveling transit. And due to the curvature and the refraction, we will have some errors. We know there will be error at point A as HA prime and at point B as HB prime. However, we don't know these 2 terms. And with that, we are able to find out the vertical distance from A to B. First of all, we will draw the level line from the leveling transit, and the difference between that level line to point A and point B will be the true elevation difference from these 2 points to the leveling transit. So we can see that for HA, we will have capital HA plus the arrow HA prime, and HB will capital HB plus HB prime. In addition, we can derive that the true elevation difference from A to B is HA minus HB. From the previous two equations, we will get HA, capital HA as HA minus HA prime, and capital HB is HB minus HB prime. So that will give you the value as HA minus HB minus HA prime minus HB prime. In general, the first term can be observed from the experiment, which comes from the readings from the rods, while for the second term, there are the errors caused by the curvature and the refraction. Usually we cannot identify the exact value of these two terms. However, we know that the combined error is in the function of the horizontal distance. If we say that AL equal to BL, then we will find HA prime equal to HB prime. In that sense, we can remove this one from the vertical distance estimation. And then we can just use the observed readings from the rods to identify the vertical distance. In addition, we know that if AL or BL is small, then HA prime and HB prime are also very small. So we can remove the term in the vertical distance measurement as compared to the actual elevation difference. This term is very small. So in general, for a small region vertical distance measurement, we can just use the observed values from the rods. Now let's see how we can use the direct leveling to find out the vertical distance between 2 points. In this example, we will place two rods at point A and B, and the leveling transit is placed in between. The reading at point A is 5.76 feet, which would be HA, and at point B is 2.33 feet, that is HB. Then we can find that the vertical distance from A to B is HA minus HB. We will ignore the potential errors caused by the curvature and the refraction. With that, we find out the vertical distance as 5.76 minus 2.33, that is 3.43 feet. So that's the way for us to use direct leveling. The next method for vertical distance measurement is differential leveling. This method will combine multiple direct leveling to determine the elevation of points some distance apart. There are some terms we need to know for differential leveling, including benchmark, temporary benchmark, turning point, backside, height of the instrument, foresight, and intermediate sight. We will introduce more details about these terms in the next few pages. This figure shows how the differential leveling is applied to determine the elevation at certain points on the Earth. In this figure, we will first start from the benchmark 1, which is the point with the known elevation. In this example, it's 72.105 feet. And then we have two turning points from the starting point. We apply the direct leveling between benchmark 1 and turning point 1. And then we have the readings at the benchmark 1, which is called backside. And another readings at turning point 1, that is defined as foresight. After that, we will move the leveling transit between turning point 1 and turning point 2. With that, we will have another backside and foresight. And finally, we will put the leveling transit at a point between turning point 2 and benchmark 2. Similarly, we will have backside and foresight. For the last one, benchmark 2, we also know the elevation of that point. And this one is usually applied for us to verify the potential errors in the differential leveling method. In addition, for all the direct leveling applied in this method, we also need to measure the height of the instrument. And this information will also be used for us to determine the actual elevation of each turning point and also applied for the error verification. Now let's see how we can process the data from the experiment. First, we are given the elevations of benchmark 1 and benchmark 2. We define them as BM1 and BM2. And from the experiment, we have some readings. From the first direct leveling, we have backside 1 and the foresight 1. We also get the backside 2 and the foresight 2 from the second reading. And similarly, we have backside 3 and the foresight 3. If we have more than 3 direct levelings applied, you can add more values. With that, we can estimate the elevation at the turning points and also the benchmark 2. For turning point 1, the elevation is benchmark 1 plus backside 1 minus foresight 1. For turning point 2, that is turning point 1 plus backside 2 minus foresight 2. And we have the estimated elevation for benchmark 2 as turning point 2 plus backside 3 minus foresight 3. So this is just the estimated value for the elevation. Finally, we can define the error as the estimated elevation at the benchmark 2 minus the true elevation of benchmark 2. Now let's see how we can record the data from the experiment and do the calculation for elevations. In this page, we have one table applied for the data recording. We will have some standard formats to record the data from the experiment. First, we will consider the benchmark 1. At benchmark 1, we will have backside 1 and the first height of the instrument. For the foresight 1, we will put in the second row. Similarly, we apply the second leveling result in the second row and third row. We have backside 2, height of instrument 2, and foresight 2. Also, we will have backside 3, height of instrument 3, and foresight 3. With that, we can do the calculation about the elevation at each location. For benchmark 1, we know that the elevation is just the benchmark 1. And the second one, that will be benchmark 1 plus backside 1 minus foresight 1. And that will be turning point 1 plus backside 2 minus foresight 2. At last, we have turning point 2 plus backside 3 minus foresight 3. Finally, we need to record the error. That is the estimated benchmark 2 minus the true benchmark 2. In general, differential leveling can be categorized into 3 types. The first one is called line leveling. So in this method, we will start from one benchmark and then go through multiple turning points, and eventually it will be ended at another benchmark, say benchmark 2. So for this experiment, we will know the true elevations at the two ends. The second one is called loop leveling. In this method, we will start from one benchmark with no elevation, and then we will go through multiple turning points. Turning point 1, turning point 2, turning point 3, turning point 4, and at last it will go back to the initial benchmark. So it will form a loop for the measurement. The third type is called open-end leveling. With that one, we will start from one benchmark and then go through multiple turning points. And in this measurement, it will end at one turning point, which we don't know the elevation of that turning point. So that's the three types of the differential leveling procedures. In differential leveling, there will be some errors caused by the curvature, refraction, and instrument operations. For example, in this figure, if the chassis leveling is not aligned perfectly, we will observe some errors caused by the alignment. And from the left side, you will see some errors from the true horizontal line. EBS will becomes DBS times sine alpha. And similarly, on the right side, you will have the error as EFS equal to DFS times sine alpha. So with these errors, we are unable to use the difference between the readings from point A and point C to identify the difference in elevations. So we want to balance the backside and foreside distance so that we can remove these errors. In this balancing method, we will put the leveling transit exactly at the middle of the 2 points A and C. In that sense, we will have DBS equal to DFS. This indicates that the arrow EBS will be the same to EFS. Then we will find that the same amount of error will be applied to the readings at the two rods. With that, we can cancel the errors from the instrument. This one is also applied for the errors caused by the curvature and refraction. So we can still apply the difference between the readings in these two rods as the true vertical distance. In some real projects, such as highway construction, we want to determine the elevations of many points along a fixed line with much shorter intervals. With that one, we need to call the profile leveling to identify the elevation of many points simultaneously. These two figures shows how the profile leveling works. From the figure at the bottom, we can see that we want to identify the elevations of more than 10 points along a straight line from the 0 point to the hub. In order to identify the elevations of these points, we will start from one benchmark, benchmark 10, and we will first define a turning point. A transit will be set in between. We will have the backside to the benchmark and foreside to the turning point. In addition, we will get some foresight to the points along the straight line. and those four sides are defined as intermediate four sides. We will use the readings from these four sides to identify the elevation of these points. In addition, we can go to check the other points along the line by moving the leveling transit from turning point 1 to the hub, and then we can get an intermediate four side for another 4 points. If you have some other points you want to determine, you can move the leveling transit and determine more turning points and cover all the possible points you want to check along the line. After that, you can get the elevations of all the points along the line and draw the elevation profile, which will be shown in the figure on the top. This table shows the data recorded from the profile leveling and the calculation of elevations. In the table, we have the first column as the station name, and the backside and the foreside for all the benchmarks and turning points. Also, we will observe the intermediate foreside for all the intermediate points. Then we can calculate the elevation for all the points in the experiment. First, for the first intermediate point, we can find out that the elevation is the benchmark plus the backside minus the intermediate foreside. In this case, that will be 30 meters plus 3.478 meters minus 3.617 meters, which will give you the value as 29.861. So that's for all the intermediate points between benchmark 30 and turning point 1. For the height of the turning point 1, it will be very similar. So this one is still the benchmark 30 plus the backside minus the foreside at turning point 1, which will give you the value as 30 meters plus 3.478 minus the foreside as 0.193, which will give you the value as 33.285 meters. And for all the intermediate points between turning point 1 and turning point 2, we need to use the elevation of turning point 1, the backside of turning point 1, and the intermediate foreside for the calculation of the elevation. And similarly will be applied for turning point 2 and turning point 3. All the intermediate points between turning point 2 and turning point 3 will need to use the elevation of turning point 2, the same backside, and the intermediate foreside for the calculation of the elevation. And once you complete all the computations, you can draw the elevation profile. The figure here shows the result from the previous table. The x-axis represents the distance of all the stations along the target line, while the y-axis shows the elevations of each intermediate point. With this speed profile, we can find out the distributions of the elevation along the target line. And this one will be very beneficial for any construction work. So that will be all about the lecture today. Thank you very much for your attention.